Corollary 8.19 is a subtle but very useful result. It says that if Ri of 0 is strictly greater than 0, then Ri of d is strictly decreasing for d between 0 and d max, and the inequality constraint in the definition of Ri of d can be replaced by an equality constraint. To prove the corollary, we first show that Ri of d is strictly greater than 0 for d greater than or equal to 0 and strictly less than d max, and this is done by contradiction. This will be achieved in a few substeps. Suppose Ri d prime is equal to 0 for some d prime greater than or equal to 0 and strictly less than d max, and let Ri d prime be achieved by some x hat. Then Ri d prime is equal to ix x hat is equal to 0, which means that x and x hat are independent. Then we show that such an x hat, which is independent of x, cannot do better than a constant estimate x hat star. That is, expectation of dx x hat is greater than or equal to expectation of dx x hat star, which is equal to d max. This is done by considering the following. First, d prime is greater than or equal to expectation of dx x hat, which is equal to summation x hat, the probability of x and x hat, times dx x hat. Since x and x hat are independent, px x hat can be written as px times px hat. Now px hat does not depend on x, and so it can be moved outside summation x, and summation x px dx x hat is simply expectation of dx x hat. This is greater than or equal to expectation of dx x hat star by the definition of x hat star, and this expectation is equal to d max, and finally we obtain d max. Thus we have shown that d prime is greater than or equal to d max. This is a contradiction because at the very beginning we assume that d prime is strictly less than d max. And therefore, we conclude that Ri of d is strictly greater than 0 for d greater than or equal to 0 and strictly less than d max. In the second step, we note that Ri of d must be strictly decreasing for d greater than or equal to 0 and less than or equal to d max. Because Ri of 0 is greater than 0, Ri of d max is equal to 0, and Ri of d is non-increasing and convex. The idea is illustrated in the following figure. Suppose Rid decreases for a while, stay constant, and then decreases to 0 at d equals d max. Then Ri of d is not convex, which is a contradiction. In other words, Ri of d cannot stay constant for a while, and so Ri of d must be strictly decreasing for d between 0 and d max. In the third step, we show that the inequality constraint in the definition of Ri of d can be replaced by an equality constraint by contradiction. Again, this is achieved in a few substeps. First, we assume that Ri of d is achieved by some x hat star, such that the expectation of dx x hat star is equal to some d prime prime, which is strictly less than d. Then Ri of d prime prime, by definition, is equal to the minimum of ix x hat over all x hat such that the expectation of dx x hat is less than or equal to d prime prime. This is less than or equal to ix x hat star because the expectation of the distortion between x and x hat star is equal to d prime prime. And by our assumption, this mutual information is equal to Ri of d. Thus, we have shown that while d prime prime is less than d, Ri d prime prime is less than or equal to Ri of d, which is a contradiction because Ri of d is strictly decreasing for d between 0 and d max. And therefore, we conclude that expectation of dx x hat star is exactly equal to d instead of strictly less than d. Thus, the inequality constraint in the definition of Ri of d can be replaced by an equality constraint. Now we have finished the proof of corollary 8.19. In this corollary, the assumption is that Ri of 0 is strictly greater than 0. This appears to be a rather restrictive assumption, but in fact it is not. The reason is that in all problems of interest, R of 0, which is equal to Ri of 0, is greater than 0, because otherwise R of d is equal to 0 for all d greater than or equal to 0, because Rd is non-negative and non-increasing. Therefore, we have Ri of d equals minimum Ix x hat over all x hat such that expectation of dx x hat is equal to d. In example 8.20, we look at a binary source. Let x be a binary random variable with probability x equals 0 equals 1 minus gamma and probability x equals 1 equals gamma. Let the reproduction alphabet be the same as the source alphabet, that is 0 and 1, and d be the Hamming distortion measure. In the following, we will determine Ri of d, the information rate distortion function. First, we consider gamma between 0 and 1/2. We will show that Ri of d is equal to hb gamma minus hb d if d is between 0 and gamma, and equals 0 if d is greater than or equal to gamma. Since gamma is equal to 1/2, that is, it is more likely that x is equal to 0, we see that x hat star, the best possible constant guess, is equal to 0. And d max is equal to expectation of d of x and this constant guess 0 is equal to probability that x is equal to 1, which is equal to gamma. Now consider any estimate x hat and let y equals the distortion between x and x hat. As d is the Hamming distortion measure, y is simply the indicator function for the error event. Now observe that conditioning on x hat, x and y determine each other. Because conditioning on x hat, if we know x, then we know whether there's an error. On the other hand, conditioning on x hat, if we know whether there's an error, we also can determine the value of x. And so, the conditional entropy of x given x hat is equal to the conditional entropy of y given x hat. Then for any x hat such that expectation of dx x hat less than or equal to d, where d is less than gamma equals d max, we have the mutual information between x and x hat, which is equal to entropy of x minus entropy of x given x hat, where entropy of x is equal to hb gamma, and entropy of x given x hat is equal to entropy of y given x hat. Now entropy of y given x hat is upper bounded by entropy of y, so with a negative sign, we obtain the lower bound hb gamma minus entropy of y. As y is the indicator function for the error event, the entropy of y is equal to hb of the probability that x is not equal to x hat. We can further obtain the lower bound hb of gamma minus hb of d, because the probability that x is not equal to x hat, that is the probability of error, is equal to the expectation of the distortion between x and x hat, which is less than or equal to d. And hb of a is increasing for a between 0 and 1/2. Thus, we have shown that for any x hat such that the expectation of dxx hat is less than or equal to d, the mutual information between x and x hat is greater than or equal to hb of gamma minus hb of d. Therefore, Ri of d, which is the minimum of the mutual information between x and x hat for all such x hat, is greater than or equal to hb of gamma minus hb of d. To prove that this lower bound is indeed tight, we need to prove that the inequalities in 1 and 2 can be tight simultaneously. Observe that the inequality in 1 is tight if and only if hy given x hat is equal to hy, that is, y is independent of x hat. And the inequality in 2 is tight if and only if the probability that x is not equal to x hat is equal to d. Now recall that in order to specify the random variable x hat, we can specify the joint distribution of x and x hat such that the marginal distribution of x is exactly equal to the given source distribution for x. Thus, we are motivated to start with the random variable x hat, pass it through a certain channel to obtain the random variable x. In order for this to work, we need to specify the distribution for x hat and the channel such that the output distribution is exactly equal to the source distribution for x. That is, the binary distribution consisting of the probability masses 1 minus gamma and gamma. Toward this end, we notice that the binary symmetric channel with crossover probability equal to d is exactly what we need, because for the BSC, the probability of the error event is independent of the input variable x hat. That is, y, the indicator function of the error event, is independent of x hat. Also, the probability that x is not equal to x hat is simply equal to d, the crossover probability. This binary symmetric channel is called a reverse binary symmetric channel. So it remains to specify a distribution for x hat such that the output distribution is exactly the given source distribution. We claim that the distribution for x hat is given by 1 minus gamma minus d divided by 1 minus 2d, and gamma minus d divided by 1 minus 2d. So let us verify that this is correct. We note that 1 minus gamma d divided by 1 minus 2d times d plus gamma minus d divided by 1 minus 2d times 1 minus d is exactly equal to gamma. We also need to verify that the input distribution is a proper distribution, namely that gamma minus d divided by 1 minus 2d is between 0 and 1, and this follows because d is less than gamma, which is less than or equal to 1/2. The details are given in the textbook. So we see that the lower bound that we have obtained for Ri of d is indeed tight. Therefore, we conclude that for gamma between 0 and 1/2, Ri of d is equal to hb of gamma minus hb of d if d is between 0 and gamma, and is equal to 0 if d is greater than or equal to gamma. For the other case, when gamma is between 1/2 and 1, by exchanging the rows of the symbols 0 and 1 and applying the same argument, we obtain Ri of d as above, except that gamma is replaced by 1 minus gamma, because in this case 1 minus gamma is between 0 and 1/2. That is, Ri of d is equal to hb 1 minus gamma minus hb of d, if d is between 0 and 1 minus gamma, and is equal to 0 if d is greater than or equal to 1 minus gamma. Instead of writing out the expression for Ri of d for two different cases, we actually can combine the two cases and obtain Ri of d equals hb of gamma minus hb of d if d is between 0 and the minimum of gamma and 1 minus gamma, and is 0 if d is greater than or equal to the minimum of gamma and 1 minus gamma for all gamma between 0 and 1. To verify that this is correct, we first check the case for gamma between 0 and 1/2. For this one, the minimum of gamma and 1 minus gamma is simply equal to gamma, and this is exactly as what we have obtained in step 7. For gamma between 1/2 and 1, the minimum of gamma and 1 minus gamma is 1 minus gamma, which is exactly the same as the bond we obtained in step 8. In addition, we notice that hb of gamma is simply hb of 1 minus gamma, and so we have verified the case for gamma between 1/2 and 1. Now for the uniform binary source, that is the case when gamma is equal to 1/2, with the Hamming distortion measure, the information rates distortion function is equal to 1 minus hb of d if d is between 0 and 1/2, and is equal to 0 if d is greater than or equal to 1/2. And this is shown in the following figure. Here is a subtle but important remark about the rate distortion theorem. The rate distortion theorem does not include the source coding theorem as a special case. In example 8.20, we have obtained this expression for the information rates distortion function Ri of d, where gamma is equal to the probability that x is equal to 1. Therefore, when d is equal to 0, we have Ri of d equals hb of gamma, because hb of d is equal to 0, which is equal to the entropy of x, that is the source entropy. By the rate distortion theorem, if R is greater than Ri of 0, that is entropy of x, the average Hamming distortion, that is the error probability per symbol, can be made arbitrarily small. However, by the source coding theorem, if R is greater than the entropy of x, the message error probability can be made arbitrarily small, which is much stronger. The reason is that in decoding the message, if one symbol is decoded incorrectly, then the whole message is decoded incorrectly. In other words, the error probability per symbol being small does not imply that the message error probability is small. On the other hand, if the message error probability is small, then the error probability per symbol must be small.